Okay, in the last Newton's second law discussion, I want to make sure that's on. In the last Newton's second law discussion, what I did was I applied a force right there. Okay. But much more typically, you would actually have something hanging there. And let's say it's 2 kilograms. Now, the problem with this is that's a multiple body problem. So you really have to solve it like we did with multiple body problems when we were doing linear motion. And the way you do that is this. Do a free body diagram or force diagram for each object. So for the pulley, there's mg. There's some support force, I'll call it the normal force. And there is tension. Be really careful. This is not pulling with 20 newtons on there. If it were pulling with 20 newtons, that means the tension is 20 newtons and mg is 20 newtons. That's not going to accelerate. So we've got those three forces. I'm going to still pick this to be the positive direction. And if you remember when we did multiple body problems, we had to be consistent in our positive direction. So I'm going to pick down positive for the 2 kilogram object. And mg is 20 newtons and tension is up. Okay? And it's going to be less than 20 newtons if this thing is going to accelerate. Okay, the easiest one to write a free body diagram, a Newton's second law for is this linear one. I'm just going to write the Newton's second law. I can't solve it, but I'm going to write it. Sum of force equals ma. Remember when we do sum of torques, it's I alpha. But what we end up with is mg minus tension equals ma. Okay? And I can plug in the numbers 20 minus t equals 2a, but I can't solve that yet because I've got two unknowns, t and a. Let me write it. 20 minus t equals 2a. Now let me come up here and write the Newton's second law equation for this. And as you might imagine, you're going to have two equations, two unknowns. Sum of torques equals I alpha. And the sum of torques, there really is only the one torque. That force tension is R away. There's 90 degrees. So you have R times tension times sine of 90, which is just 1, equals I 1/2 mr squared for a disc or a pulley times alpha. Okay? Well, we've got the R's there, we've got the T. I'm going to start plugging in numbers. You can do it this way, but I'm going to show you later how this is actually made much easier. 1 times R squared, that's 0.25, divided by 2 is 0.125 alpha. So, if we look at that, and let me divide by 0.5, in other words, multiply both sides by 2, T equals 0.25 alpha. So we've got two equations, 1, 2, 3 unknowns. But we do know that A equals R alpha. The linear acceleration is going to be R times alpha because it's R, and in this case that is the radius, away from the center. So we can substitute in now. A equals R alpha. Alpha is A divided by R. T equals 0.25 times A over R. R is 0.5. Divide by 0.5. This ends up being T equals 0.5 A. Now I can do a couple of things. I can use 0.5 alpha and substitute it, 0.5 A and substitute it in there. And so I have 20 minus 0.5 A equals 2A. If I add 0.5 to both sides, I get 2.5 A. 20 equals 2.5 A. And that ends up being, let me think about that, 5 divided by 2. 40 divided by 5, A equals 8 meters per second squared. Okay? Alpha would be 8 divided by 0.5. And so alpha would be 16 radians per second squared. So we can just start plugging in numbers and solving things. This is a very important step. A equals R alpha. It's the way that we get between the linear and the angular, the rotational. I'm going to jump back. I'm going to erase a lot of stuff. And what I'm going to do is I'm going to do this with only variables to show you that it actually works out kind of nicely. Okay, so my linear Newton's second law hasn't changed. mg minus t equals ma. And I'm going to do this rf sine of 90, which is 1. And I'm sorry, rf, and this is actually the tension, equals I, and I'm going to leave it as a variable, mr squared over 2, times alpha. And remember, this is a really key substitution. So what I'm going to do is I'm going to say alpha is A over R. A over R. Every time you've got a multiple body problem with rotation, and you've got some stuff moving linearly, some stuff moving rotationally, you're going to want to use that substitution. Now I could have made this R alpha and solved for alpha, but for some reason I like to do this, and that reason is this. Look what happens. I could multiply both sides by R. I'd have R squared, and they cancel. Or I get R squared divided by R is R, cancels out an R on the other side. So all these R's cancel out, and you just end up with a really simple expression. MA over 2. Okay? That's one thing. Now another thing is I could just put that right in there. But one of the ways when we have multiple bodies, and if I had another pulley on the other side, if I had an Atwood machine pulley, if I had another mass on the other side, if I had an Atwood machine, I'd have 3 equations. And it becomes a little harder to substitute in. But one of the things I like to do is I like to write this down here, MA over 2, and then I add the 2 equations. If left equals right, then left plus this left equals this plus this. So when I add them together, mg, and by the way, this is the mass at the falling. I'm going to call this m1, and I'm going to call this m2. So m1g equals ma plus ma over 2, 3 m2a over 2. And then we can solve for that acceleration. The acceleration, the linear acceleration, is going to be 2/3 m1 over m2, m1g over m2. I'm missing an m1 somewhere. That's because this is m1 and this is m2. I'm going too fast. m1g, m1a, let's do that. So I'm sorry, this whole thing was wrong. And what happens is this ends up, when I add those 2 together, I get m1g equals, you can think of that as the net force. Okay, m1g, the net force on the system, equals m1a plus m2 over 2 times a. We can factor out the m1 plus m2 over 2, and you get m1g over m1 plus m2 over 2. If we think back to how these things traditionally look, m1g is the thing that accelerates the system. That's that net external force that accelerates the system. m1, well, yeah, that's what needs to be accelerated in a linear way. And this is an expression, this is something that's related to how hard it is to turn that disk, how hard it is to rotate that disk. So this makes some intuitive sense. m1g over m1 plus m2 over 2. So we can do that and get a variable-only answer. And in the next video, I'll go one step farther. And I'll go for an Atwood machine where you've got 2 different things going on there. You've got 2 masses hanging off.